Yeah, so fortunately or unfortunately, our brain works that way. If we have a little bit of information, then we want to complete that information. We want to get more and get a complete set of information. So whenever you are all in school, so when you learn, if you could read a little bit beforehand, if you could think about beforehand, then it really helps. Say, for example, if you think about building a bridge, designing a bridge, this course will be much more easier for you to appreciate. That's great work there. I can tell you, when you design a bridge, being engineers, we always look at, the forces acting on the bridge. That's most important. That's based on the forces you can design the bridge. What kind of load are you going to? Is a bridge for humans to walk? Then you don't have to have a big bridge, right? Just humans walking. The load is going to be very minimal. But if you have to have a huge truck passing on the truck on the bridge, you need a pretty big bridge, and you need a strong bridge because you are going to load it with hundreds of tons, right? So the loads and all the other forces acting on the bridge is most important parameter we consider. Like the wind load, if it is going to be across a river, then the water is another consideration. So you have to consider all sorts of loads, kind of dynamic loads, then the static loads. Dynamic loads means moving loads. If the truck is moving, that's dynamic. But then static means something that's not moving. So the load itself of the bridge, and then the soil conditions. So those are the parameters we consider. So just think about it. Our intention is not to build a bridge or anything, but to think about how engineers consider, designing, building, and operating stuff. Yeah, Hari?
Yes, sir. Like parameters like to be considered:
Yeah.
the terrain on which the bridge is built,
Very
the
good.
size and weight of the bridge,
Excellent.
the amount of weight the bridge can carry,
Oh, yeah, very good.
the, the height at which the bridge elevates, the material according to the lifespan of the bridge, like temporary, permanent bridge,
Oh, yeah, very good.
the weather in the region where the bridge is built, the cost of construction, and weight distribution.
Excellent work.
Thank you, sir.
So those are the major considerations. Yes. So see, from here, this is what you should understand. This is the same way, very nice. So this is the same way we design and build other things. It's not just the bridge. Anything you design and build, this is the philosophy. That's what we're talking about. Who else was the next one?
Yes, sir. So mine with the same points as Hari's. I don't think I did anything different. Like I too said the location of the bridge, the dimensions, the width, the height, the maximum load it should be able to take. Depends on what kind of vehicle it's allowing. If it's only cars, or if it's truck too, or if it's just a pedestrian bridge,
Yeah,
and the materials for construction and the
yeah.
cost.
Excellent. See, so you guys are getting the hang of it, right? So, though you guys are not engineers, you already understand how engineers look at things and design and build stuff, right? So this is why I gave this exercise, basically to do a thought. This is a thought experiment kind of a thing, right? Like you think about and then come up with ideas. So excellent. So in the last couple of classes, we talked about the process, the engineering design process, right? How engineers follow a process. So we talked about this already. Whatever you're designing, even if you're designing a pen or a Ferrari or an Eiffel Tower, the process is the same. That's the most important thing we all should appreciate. The process, you come up with the definition of the problem, then you do the background research, whatever you're designing, and then specify the requirements, what you exactly want to be designed. That's one thing about engineering. It has to be exact. We don't really go by something like, okay, it has to be a nice car. No, that's not the way we design. We have to have exact. If that's a car, what's the dimension of the car? What's the speed? what's the weight. Every single detail of, the requirements must be frozen first before you start designing. And then once you know the requirements, you brainstorm and come up with ideas, and then develop a prototype solution, then test the prototype. You want to know if this thing is going to work, right? You can design anything and build anything, but then does it work? And then once you know this prototype works, you can definitely, it's an iterative process. You may have to go back and work it, and then finally you come up with a final product, and then you communicate the design. You have all the drawings and specifications and operating procedure, everything. So that's the way we design anything, for that matter. So now, this is the engineering process. To do this, you need a lot of knowledge. You need a lot of, as I said, skills. You need a lot of, that's what you're going to learn in a college of engineering, if you go to a college of engineering, right? Because you need to know a lot of things to do this process. It's not that easy. So you need some techniques, you need some skills, you need a lot of knowledge of sciences, math, all sorts of things. So that's why you go to a college of engineering and learn all those things, and then you start practicing engineering. So any question on the engineering process? So as I said,
I have a doubt.
Yeah, go ahead.
Sir, so like the design or the creating the prototype for the final product, that'll be by the architects, or who will do the prototypes? Who will do the prototypes for the final product?
The prototypes are designed and built by the same engineers, because the prototype is like a prototype of the final product, right? So we, for example, when we build a plant, we first build a pilot plant, for a chemical plant. We build a pilot plant, and then we learn about that pilot plant, then we scale up. So we ourselves design and build it, but then we take a lot of help from technicians to build actual building process. Is that you meant, or?
Yes, sir. I wanted to know who will do the prototypes.
Yeah, we design and we work with technicians. The actual building will be done by technicians, right? Because usually we don't turn the wrench, but we'll have a lot of technicians. For example, when we built an engine, when I was in GE, we designed and built a new engine from scratch, from the drawing table. So we built many prototype engines, not one. We built at least 10 or 15 different prototype engines, and then we tested those engines in our test beds, and we found out, we are failing many components, and then we redesigned that component, because if you look at an engine, there are so many different components, right? So we would fail some component, and then we redesigned that one, and then we build another prototype. So it took us 5 years to build that engine. Usually to design and develop an engine, it takes a car engine or any engine for them, it takes about 5 years.
Okay, sir.
Yeah. Good question. Excellent question. So as I said, to do that process, to do that engineering process, you need to know a lot of things, and you need to have skills and knowledge. So that's what I call it 4 pillars of engineering. The 4 pillars of engineering, these are the things you need to learn. You need to have, first pillar is methodical approach. So the 4 pillars of engineering are methodical approach, practical skills, abstraction, and creativity. We already talked about these a little bit. Methodical approach, as you know, engineers are always methodical. They follow a process. As I said, the engineering design process, and doing anything and everything, you need to have a real good methodical approach. I'll explain this. And then practical skills. Engineering, as I said, engineering is completely practical. If you have to design and develop and build something, you need to have those practical skills. So it's practical. Then abstraction, which is math and science, because you need to do a lot of calculations. Because you cannot do trial and error. If you're designing anything, what you do is you are going to calculate how much force, how much energy, how much electricity, how much, what's the velocity, all sorts of calculations are required. And for that, you need to know the required math and science. You don't need to be a mathematician, you don't need to be a physicist, but you need to understand math and science. And then creativity, as I said, engineers are creative, right? Engineers created most of the world we see today. So that in the natural world, we didn't have a house, we didn't have a car, we didn't have clothes, we didn't have anything. We created all these. So engineers are creative. So creativity is extremely, extremely important in engineering. So those are the 4 pillars of engineering. Now I will explain these through a story. Actually, let's move ahead and think about a story. Okay. How many of you know these guys?
Right brothers. Right brothers.
Yeah, exactly. Wright brothers. What did they do?
Found
An airplane. Build
Yeah,
an airplane.
they invented airplane, right?
Yes.
So what's an invention? They invented aeroplane. So aeroplane was an invention by the Wright brothers. So what is an
Building
invention?
something new for the first time, and it's unique.
Exactly. Yeah, something that was, creating something that was not there before. That's invention, right? Completely new thing. It's an invention. So what's discovery then?
finding a thing that
Finding a thing which already exists.
Yeah. What's an example?
finding a new star, black hole.
Oh yeah, exactly.
Or a new
finding
organism.
organism. You find a new variant of. They discovered a few different variants of coronavirus, right? They didn't invent it, but then if you invent, somebody invented an iPhone, right? Because an iPhone wasn't there in the first place. So they invented aeroplane. So Orville and Wilbur Wright, and what you see here is the first flight. Fortunately, a photographer was available, and they captured that moment in December 17, 1903, the first flight. That was just 12 seconds, right? 12 seconds. That was the first flight. Today, we can fly, people have flown even 24 hours without stop. So, and you can see Wilbur Wright standing there, and Orville is actually lying on the plane. That's the way they used to control the plane. Okay, so we'll look into a little bit of the aviation history. So this was the first plane. They improved the plane. Now you can see actually Orville sitting on it. They improved the plane further, and then they put a seat. They were able to control it that way. Next. And what were they? Do you know what these guys were doing before they invented the plane?
What's so?
Cycle mechanic.
Yeah, they were bicycle mechanics. And this is the bicycle you see is the actual, the bicycle they built. And actually, I think I took this picture at the Wright Brothers Museum. You know, this is the bicycle, and those days in late 1800s and close to 1900, bicycle was a huge revolution because the personal transport wasn't available. They were using horse buggies, right? Horse buggies and horses were the biggest. In 1900 in New York City, there were more than 300,000 horses and horse buggies, you know, in New York City. Today, I don't know if you have 5 horse buggies in whole entire New York City. So that used to be the mode of transport, but then bicycles became a huge hit those days. And then these guys made a fortune making bicycles. They were great mechanics. And you won't believe this bicycle there was costing $50. those days, and $50 was huge amount of money those days. It was like today's dollars, it could be easily about $5,000, you know. So and I can tell you, you go to Walmart, you can buy a decent bicycle for $50 today. So these were those guys were great bicycle mechanics, and then they started to solve this huge problem called flying. Next. So in about 1500s, Leonardo da Vinci. Have you heard of Leonardo da Vinci?
Yes, sir.
Da Vinci made these kind of drawings, and he tried flying actually, but then until about 1800s, people thought you need to have a flapping wing to, just like we were modeling after birds, obviously, right? People were observing the birds and how birds were flying, and humans always wanted to fly. That was the dream for thousands of years. And then Da Vinci made these kind of drawings, but then when he tried this, the biggest thing was that, we didn't understand the aerodynamics, or we didn't understand, we didn't have a mechanical power, right? So he knew it's not going to be, humans cannot really, people tried having, just putting a wing on your shoulders and trying to flap it, and fail miserably because you're so, humans are heavy, very heavy, right? It's not like the birds, they're light, very light. And they have huge wings for the size of their body. So we can do that. We can have a huge wing flapping. It's impossible for us to do. And then we didn't have mechanical power to do it when Da Vinci was trying this. Next. So we understood, being humans, we are very, very creative. We are very ingenious, and then we came up with hydrogen balloons in 1783 and hot air balloons. We understood this thing called hydrogen is much lighter than air, and then hot air, if you can heat the air becomes thinner and it's lighter than the cold air, right? So have you seen hot air balloons?
Yes.
Yeah. Today, even for kind of fun, people use hot air balloons even today, right? People don't use hydrogen balloons anymore. But then these kind of blimps you can use, and then there it is lighter than air. The big thing you notice here must be the size of it and how many people can travel. If you have a huge, massive balloon, like a size of your house, maybe 2 people, it can carry 2 people, right? So it's not like a Airbus 380 where they can carry 600 people on board, right? And it's not like that. These balloons are as big as 380, but then they can carry only a couple people, or at the most maybe 10 people. And then what are the other limitations of the balloons?
It can't fly as fast as an airplane.
Exactly. There you go. They can't go very fast. They have to be very, very slow, like a snail pace kind of a. Today we can go supersonic, right? Some of our fighter jets can fly supersonic. When you say supersonic, faster than sound, right? So many fighter jets go supersonic, and the rockets definitely hit much higher speeds than sound. So speed matters. Otherwise, when are you going to get from one place to another? So this was for fun. People enjoyed it, and even today people use it for fun. But this was not a solution for our flying problem. Then things started changing actually when Sir George Cayley came up with different ideas. Instead of a flapping wing, he came up with fixed wings. And he started thinking about aerodynamics for the first time. Being an engineer, he was a great engineer. He built a lot of stuff in England. So, and then, you know, the industrial revolution was underway in England, right? So in 1800s, industrial revolution uh, happened. So it was a huge thing, and there was money, there was a lot of scientific things going on. Actually, the scientific revolution and the industrial revolution went hand in hand, one complementing the other. So at that time, uh, he came up with the idea of fixed wings. That changed the whole thing, actually. But then from 1809 to about 1900, the biggest problem was that we did have mechanical power, but the mechanical power available was, what was the mechanical power available in 1800s? What kind of mechanical power, an engine or anything they used? The Industrial Revolution was powered by steel and steam. That's what they say, steam. So they had steam engines. But then unfortunately, steam engines are so huge that you cannot use them on an aircraft, can you? So
Also, you can't because they are heavy.
yeah, they're huge, they're massive, right? So on a locomotive, you know, most of the locomotives in the world were in 1800s and even early 1900s were using steam engines. But then locomotives are so huge, big, they can afford to do that, but then planes cannot. So though Sir Cayley had a lot of ideas and he came up with all these fixed wings, aerodynamics, the lift, you know, how planes can lift and how the drag works. And he predicted powered flight, but then unfortunately, those days they didn't have a lighter mechanical power available to them. And in 1886, Nicholas Otto came up with a spark ignition engine, a petrol engine, right? And then the whole entire equation changed. From there, people thought, okay, now we can power these things with a petrol engine. Or then Rudolf Diesel came up with this diesel engine in about 10 years, in almost 1890s, he came up with that. So engines were available towards the end of 1800s, close to 1900. So that changed the equations. So in 1895, Otto Lilienthal actually flew his, this is not a powered flight. Lilienthal didn't try powered flight. He was trying, you know, just flyers without any, in the wind. He would jump from a hill, and he was trying to fly and control his plane. Unfortunately, he didn't have proper control over it, and in an accident, he died. But Lilienthal calculated a lot of things like lift and drag, and he came up with much more better equations to do those calculations from his experiments. He was a German. So Lilienthal was a pioneer of flight too. And then Samuel Langley, as I said, Langley tried something very difficult. What you can see is he built a huge plane with a steam engine, but then it was too heavy that it could never lift off the ground. So, and then he didn't have any control over it. So though Langley tried all sorts of things, he had a lot of money because he was a great engineer. He was working with the U.S. Army. He had plenty of money, but then he couldn't lift off the ground. And then there was another guy called Octave. He was an engineer too. So he was trying the biplane, but then he also failed to control, and he couldn't really progress his plane either. Then came our guys. Here you go in 1903 in December. They tried first with their flyers without the power, you know, no propeller, no power to the left. What you're seeing is no propeller, just the flyer, you know. But what these guys did was they tried to control, they thought about controlling the plane first before trying a powered flight. That was the greatest thing they ever did. They didn't go with the powered flight first. Instead, they built their flyer and they tried to control the flyer. So control is most important, right? Because a plane is the most unstable thing in the air if you look at. So they understood this and they came up with a three-way control system. That's the way they control their flyer. And once they were sure about their controls, they added power, and then they succeeded. You can see at the same time, almost same time, 1903, some people say Alberto Santos Dumont was the first one to invent the plane. But then Wright brothers did it a little earlier, and people knew about it. But the Wright brothers really recorded everything very, very well. So they are supposed to be the inventors. But then Santos Dumont in France had done this too. So next, you can see Santos Dumont flying his plane here. It was also a biplane, but then he had the elevator in front, and he's flying it standing. You can see that this is in France, in Paris actually. So he at the very same time, like 1903 to 1905, he did fly, and then he landed successfully. So. And you can see the story, you know, as I said before, we saw that picture where, you know, it's a historic picture where Wilbur is standing there and Orwell is flying the plane with power. And what you see is the first flyer. It's model to the right. What you see is the first model of the flyer. It's unbelievable. I have seen the actual flyer in the Wright Brothers Museum in Dayton, Ohio. One of the flyers they built, and then there's an actual flyer sitting in Smithsonian Museum in Washington, D.C. So yeah, you can see those actual stuff they made. It's unbelievable. Just with wood, you know, spruce wood and turp, they made a plane. Today, you know, planes are so sophisticated, and we can't even think about having a plane like this, right? It's so fragile, and it's incredible. This thing flew. It's interesting to know about these. So read about the inventions. That'll be great for you guys. If you look at the plane, as I said, the most important thing is about controlling the plane. You know, actually, you are controlling the car only in one axis. You are only controlling that in the yaw, right? But then if you're taking a turn, when you take a big turn in a car, actually the car rolls a little bit. If you're taking a left turn, the car rolls a little bit towards left. And then if you're taking a right turn, it rolls a little bit towards right? Have you noticed that? Exactly. And so there are two axes of control, right? You need to control these two. And if you cannot control the roll of the car, it's going to tip over, right? That can happen. Or if you're riding a bicycle, actually you're controlling the bicycle in two axes. One is the yaw. If you have a pedal, you're turning, I mean, if you have the handlebar, you turn the handlebar left or right, and you control the yaw, right? You turn left or right. And then when you're riding the bike, what are you doing? When you're riding a bike, you are adjusting your weight, you know, and controlling the roll, rolling left or rolling right. Correct? So these are the things. But if you have a plane, you have a third axis, which is the pitch of the plane, right? The plane can go this way. The nose can go down, or the nose can go up, right? When it takes off, the nose is up, right? And when it is landing, the nose is a little bit down, and then right when they land, they pull the nose up. So plane has to be controlled in all three axes. This is where the Wright brothers were most successful. Nobody else thought about controlling the plane in three different axes. That's exactly they did. You have to control the yaw, turning left or right. Any moving thing you have to control that way. And then the roll, if I'm going this way or this way, and then the pitch, the nose down or nose up. So this is the way they started controlling the plane, the flyer actually. That's why they were successful. They were able to control all these, and then they could fly stable up in the air. So that's what they did. And you know what? Where did they get this idea from? Do you know where they got this idea from? Any guess? What was their original profession?
Bicycle.
Bicycle mechanic.
Yeah, they were bicycle mechanics. So they got the idea from the bicycle because they thought bicycle is an inherently unstable kind of a vehicle, right? You all ride bicycle, right? And it's very unstable. If you don't control your weight very, very well, you're going to fall off, right? So they understood if bicycle is unstable, they started thinking about how do we control a bicycle? Okay, we control the yaw, we control the roll too. But then they understood, okay, for a plane, there's a third axis. And then they got this idea, if a bicycle is unstable and if we're able to control an unstable vehicle very, very well, a plane that is unstable in the air can be controlled. This is where they got the idea. So it may be a coincidence, but then they got the idea from the bicycle to a plane. It's incredible, right? That's what genius people do. They can connect dots that nobody else sees, right? Nobody else thought about a plane. There's a connection between a plane and a bicycle. Nobody else thought, but they were super geniuses. They were able to connect those dots, and rest is history, right? So what they did was, if you look at how did they go about solving the whole entire problem of flying? This is a classic example of a design and development that an engineer would do. They were not trained engineers, but they were geniuses. They were real. I would say they were one of the best, greatest engineers we ever had. So what they did was, they studied the problem extremely well. What is the problem? As I said, they studied the stability, they studied all sorts of things, and they understood the state of the art. They learned so much from Lilienthal. They learned so much from Sir Cayley's equations. And then they defined the problem very, very well. They defined the problem as what? A problem of control. Nobody else defined the problem as the problem of control. That's where, if you have the clarity of thought, if you can define a problem very, very well, then solving that problem is very, very easy. Even when you sit down and solve a mathematical problem, if you really know, if you can define what this problem is all about, or if you don't know what exactly the ask is, find x from a find a y from a graph, and you don't know what exactly to be found, it's hard. But then once you know exactly what you're trying to accomplish, then it becomes much more easier. So always, if you are about to solve a problem, go ahead and define that problem as best as you can. That's the first thing. Next, Satish. As I said, they defined the problem as a problem of control, and they came up with the 3-axis control. And then they solved that 3-axis control. That's the way they went about. And first, they didn't, as I said, no power flight until they perfected the controls. They knew no point in powering up if it's going to crash every other second, right? So they did that. And one great thing about, if you read about Wright brothers or any great engineers or scientists or anybody, most important striking thing is the documentation. Man, they have documented every single experiment that they did in Kitty Hawk or anywhere. They have documented minute details, even the temperature that day, day's temperature, the wind speeds that day, wind direction, and every detail of the design of their plane. If they changed a small thing on the plane that day, they documented exactly what change they made, why did they make that change, from what time to what time they flew. Everything is documented. So that's a methodical approach for an engineer, because documentation is extremely important. If something succeeds, you can go back and understand why I succeeded if you have the documentation. But if you don't have the documentation, you will not even know why I succeeded. What was the wingspan? What was the wind speed? I don't know. Then why did I succeed? I will not know. But if you succeeded, if you know every single detail, what was the wingspan I used for my plane? What's the wind speed? And what kind of temperatures, what kind of atmospheric pressure? If you know all these, then you know why you succeeded. On the contrary, when you design something and build something for the first time, you're going to fail. So if you failed, if you have documentation, you can go back and see why exactly you failed, where exactly you failed, and you can again improve upon that particular thing. As I said, when we designed engines, you know, we used to fail component after component after component, but we had every documentation of that component, the material, the dimensions, and every detail of those components. And then we go back and study that component failure, and we know why that component failed, and then we reiterate, you know, we rebuild that component. But if we don't have that kind of documentation, we cannot do you know, the troubleshooting or come back and rebuild it. So in engineering, or anything for that matter in your life, documentation is extremely important. You know, they, as I said, they had pictures. They used to take pictures after picture, and then drawings. They had every detail of you know, detailed drawings, and diaries. Their diaries are unbelievable. They have, you know, you can, if you read through their diaries, it's incredible how well they documented. Basically, Wilbur was a great documentation expert. So it was unbelievable. And then in 1901, their glider failed to provide enough lift completely. And then they were able to go back and understand, you know, why it failed, because of their documentation. To the next one, yeah. So the first pillar of engineering is methodical approach. So this is extremely important. Being methodical is extremely important in engineering. So that's the first thing you need to learn. Be methodical, document everything, follow processes. This is extremely important. And then, you know, if you look at, they were great mechanics. So they built the engine by themselves. Everything they built the flyer using, you know, wood and tar, and they built the frame. They stitched, you know, the whole entire tarp there. You can still see the sewing machine they used in Carillon Park. It's there. They themselves used the sewing machine, and they stitched all the wings and things like that. They built the propellers from wood. They used the best kind of woods available, but then they copied these kind of propellers from boats. You know, those days people were using steamboats. So from the steamboats, they copied those propellers, and they, of course, they innovated on those. They changed some of the parameters on the propellers, but then they built the propellers. Then they built a wind tunnel. I'll talk about the wind tunnel in a minute, but then they built a wind tunnel to test different types of wings and drag and all those things. And then they built an engine, because those days when they were looking for engines, most of the engines were very heavy. So they built an engine by themselves. They bought some components and they got a good mechanic and they put together an engine for their machine, you know. So that was a great thing. They built an engine those days that was much lighter. They used you know, aluminum body, and then those days the people were using cast iron, and those engines were very heavy for flying. So they built an engine. So one thing you can see in all these is they had so much of practical skills. If they have to build something, they can build a prototype, and then if they have to test something, they can test by themselves. And if they have to do an experiment, you know, like a wind tunnel experiment, they were able to build an experiment. So that changed the whole equation. That changed everything. Though everyone on the planet wanted to fly, these guys were able to do it because they had the skills, the practical skills. So the second pillar, as I said, is practical skills. Without practical skills, you know, and you may be thinking, do I have all the practical skills today? No, that's what you're going to learn at a College of Engineering and then on your job. You know, engineers usually learn so much on their job, actually. All these kind of practical skills you learn, quite a bit of practical skills you learn on the job. Yeah, as I said, you have to be good at building. You can go through this, understanding the working of mechanisms, testing and experimentation, you know. So I would say if you want to be engineers, start messing with things, start building something, you know, small electronic things, small machines, you know, small gadgets, or if you like, you know, chemical engineering, do some reactions, but then be very safe. Don't explode things, okay? Don't blow up things. So you have to be very safe whenever you do anything. Whenever there is energy involved, be very careful, especially electrical energy or chemical energy involved. Be very careful. First and foremost is safety, but try doing things, try messing up things, you know. That's the way you can become an engineer. And when you do things, you get a lot of ideas about the theory. Why should this work? Why does this work? How does this work? You know, and then you will think about the mechanisms, and that's the way your brain appreciate things. And then we come to abstraction. Actually, abstraction is important. Actually, the Wright brothers wouldn't be successful without the knowledge of science, without the use of science. What did they do? They calculated the lift using this equation. Ks, you don't have to worry about the equation at all. It's an empirical equation derived by Cayley and other people, you know. And then there were some constants used. This was an empirical equation, practically derived. It's not exactly derived theoretically. It was derived practically. It's proportional to the, you know, the lift in pounds is proportional to the coefficient of air pressure, total area of the wingspan, you know, and then velocity of wind velocity, and then coefficient of lift. So when they failed in 1901, these guys understood that there is something wrong with their calculation of the lift. And then what they did was they decided to do an experiment and find out if, you know, actually per this equation, do you really get the kind of lift? So they built a wind tunnel where you have a fan sitting in one side, you know, you can see the fan here, and then and push wind through that tunnel. And you can put different small wings, you know, prototype wings, and then you can see how much lift happens on that wings. That's an ingenious instrument. If you see that instrument, they built in 1901 or 1902, 1901, I think. It's unbelievable the way they built it. Those guys, Wilbur and Orville, built this machine, this wind tunnel, and they tested these wings, and they understood that there was a big error in the coefficient of lift. And they recalculated those coefficients, and then they redesigned their flyer. Here you go, in 1903, you know, their flyer started flying properly. They got enough lift, and they knew how to control it. So, you know, in 1901, when they failed miserably, actually, Wilbur said, I don't think humans will fly in my lifetime, right? But then, but being Wright brothers, they were not going to give up flying. They went back home, and Wilbur was thinking how I can test this. See, this is what most of every engineer does testing. As we speak, I'm an engineer. I'm testing a lot of things today. I'm a product development engineer. I'm testing my products in many labs in the world. I'm testing some of my products in Germany. I'm testing some products in the US. I'm testing some products in Japan. So being engineers, we need to test a lot of things. That's the way we learn about our product, our performance, and we have to form experiments. We have to come up with experiments. That's where, if you have to come up with an experiment, if you're a theoretician, it's impossible to come up with a proper experiment. You need to have a lot of practical experience, and you need to know the science behind it, how these things work. But then you don't have to be a scientist, but you need to understand how this works. Then you can come up with an experiment to understand these things, and then do your calculations, and then you can build a proper product. So that's where science and math are very, very, very useful. So the third pillar is abstraction. Think about it. If you don't have this equation, how on earth can you build an airplane? How do you know what kind of wingspan you need? How do you know what kind of wind speed you need? You just can't build an airplane without that particular equation there. Any question on math and science? We'll finish with creativity, actually. And then they were very, very, very creative. In creating all these things, you can see they had only one engine, and they had two propellers in both sides. And can you see that picture right there? The pulleys. One is rotating in one direction, and the other is rotating in the other direction. They just twisted that chain, and they got both rotating in one direction, right? Sorry, in different directions. So that's the creativity these guys had. They used the same engines, one shaft to drive two propellers, using a simple thing. Just twist that chain, and then you can get a opposite direction. The big one is the engine driving, and the small one is a propeller. So you can get two different directions. You can rotate the. So next, and then the wing warping. They were extremely creative to control the roll of the engine of the plane. They use the wing warping. You can change the wing shape, lift one wing. You can see lifting the one wing and lowering the other wing. Then you get huge kind of roll. You can control the roll beautifully using the wing warping mechanism. And even today, the planes are controlled using wing warping mechanism, So, and then they built the elevator. You can control the pitch using the elevators and the 3-axis control system. So they were very, 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 very creative. So that's how engineers are. We need to be creative in our job. That's what we always think about. Innovate. At least, see, inventions come once in a blue moon. It doesn't happen every time. But then you, in your job, in engineers, most of the time what you do is innovate. You have a product, you have technology available. Using that technology, can you innovate? Can you come up with a new product? Not an invention, but then using the same technology available, you can always improve upon, same thing. Like classic example of innovation is an airplane, right? They built an airplane with tarp and wood, but then people innovated. People came up with a metal plane. People came up with like single plane instead of the biplane. Now we don't use a biplane. We use single plane. Just one wing. No two layer wings. Just one layer wings. And people came up with different engines. People came up with different capacity, bigger. So it's all innovation. Nobody invented a plane anymore. They don't have to reinvent, but then that's innovation. So if you have to innovate, you have to be creative. You need to think about your product and come up with new things. So that's the way. So creativity is the fourth pillar. It's extremely important to be creative. So those are the four pillars of engineering I wanted to talk to you about. Questions? And then in the next class, we are going to talk about career, what engineering career is, and how you can, when you go to a college of engineering, I would like you folks to ask me questions, more than I telling you what, because what are your concerns, if you can type in the course website also, that'll be great. What are your concerns when you go to a college of engineering? What concerns you have, or if you take up an engineering career, what kind of concerns or expectations you have. That would be awesome.
So practically, the Wright brothers risked their life to for flying this, inventing this aircraft, right?
Yeah, they did. Actually, they all met with a very bad accident. Also, they crashed when they were testing. They were doing a demonstration for the U.S. Army. Actually, the propeller broke into two pieces. There was this propeller cracked, and that was a terrible accident. He escaped miraculously, and he had a co-passenger. Unfortunately, a Navy officer. He died. So that was the first airline casualty. That officer, unfortunately, he died, and pretty much Orville broke his hand, leg, all sorts of. So yeah, they risked their life when they were flying. Yes, it was.